What happens when we try to graph the following function with a standard zoom? We have p of x, our parent function, equal x squared. Well, here we have it right here. As we can see the vertex quite nicely. We can see it goes up on the left, up on the right. No issues. Now what happens when we try to graph this function on a graph with a standard zoom? We're going to take the same function, but we're going to subtract 3 from the x value. We're going to take that and square that quantity. Okay, so we can actually still see the graph. So here, the purple is the parent graph, green is the transform graph, x minus 3 squared. We can still see the graph. We can still see the vertex of the parabola. Everything looks great, right? Now, a couple things to note. For the original graph, when we plug in 2, we get 4. For the new graph, in order to get 4 back, we have to actually plug in 5. Now, if we zoom out here a little bit, from the original graph, if we plug in 3, we get 9. For the new graph, we plug in 6, we get 9. So we have to plug in a bigger x value to get that. Now, we're still pretty good with x minus 3 squared. Let's change it up a little bit more than that. What happens when we try to graph this function on a graph with a standard zoom? So now let's try x minus 20 squared. Okay, now we're going to try to graph x minus 20 quantity squared. Now see, what happens is that the graph goes completely off of our standard zoom. And so if we try to plug in, let's say, -2, -1, 0, 1, and 2, some basic x values that we used for our parent function, we can see that we're not going to get any y values back that are remotely close to being on the graph. The problem is we have to actually drag all the way over here before we can see the graph. So the issue is we want to always be able to know which x values to plug in so that we can find our vertex and we can find some of these identifiable points. Otherwise, it just becomes a guessing game. So this is not easy to graph, and nor is it going to show up on a standard zoom. In fact, if we just try to plug in 0, which is where our original vertex is, we get 400 back. Yes, if we go back to our graph, if we were to plug in 0, we'd get 400 back. Just imagine how much we'd have to zoom out to figure out that point. From this, we can see that it is important to be able to know where the vertex of the graph is located on the coordinate plane. And that's not just for quadratic functions, by the way. There's a lot of different types of functions that have a lot of different identifiable points or critical points on the graph. So it's not just the vertex game for the parabola. It's a lot of different graphs have a lot of different important points, and we need to have some kind of standard way of knowing how to graph them given any transformation from the parent graph, and we can't just plug in x values. In fact, there is a way to know this algebraically, and that's why function transformations are important. So in the next video, we will be taking a look at our first function transformation called horizontal shift, and how we can actually figure out how to graph a function given its horizontal transformation. Even if it's something as big as x minus 20 squared, we can actually just make up a chart and figure out where exactly the vertex of that graph is going to be without having to just guess at which x values to plug in. That's why function transformations are important. If you have any other questions about this video, let me know.